Welcome back to Beyond the Comfort Zone Talking Shit with KING-KAMBUF. Today, we're doing something a little different. We're stepping right inside the curriculum.
That's right. This session is pulled directly from the daily lecture and assignment for the master's and PhD students at the Design and Build School of KAMBUF.
So this is for the future leaders in architecture, civil engineering, and urban planning.
It's that intersection where the big, grand architectural idea smashes right into the most unforgiving force in nature.
And our focus today is very specific: seismic system selection for what has to be the most common building type in our cities right now. The mid-rise mixed-use podium building.
It really is.
That exact model, right? The heavy concrete block for retail at the bottom, and then the lighter residential tower stacked right on top. It's the engine of urban density.
But it's also an engine of immediate and very complex structural challenges.
Which brings us to the core question, the one we can't avoid. When the design is done, the building is up, and the ground starts to shake, what actually happens? What's the mechanism that lets this thing sway and, more importantly, survive?
Exactly. And for anyone operating at that leadership level, what we call the architect, builder, statesman, seismic design is so much more than just hitting the minimum code requirements. It's a strategic civic duty.
A civic duty? How so?
Well, the decisions we're about to dissect, they don't just determine life safety, that's the baseline. They determine the resilience, the speed of recovery for an entire community after a disaster.
So our mission today is pretty clear. We are diving deep into the systems, the frames, the shear wall, the dual systems. We're exploring all the strategic trade-offs that come with each one.
And we'll trace that path. We'll start with the hard constraints of the building code, the seismic design category. Then we'll move through the complex geometry of how these buildings can fail. And we'll end on the ethics, the ethical commitment that's required to build for true civic resilience.
Before we jump in, let's frame this challenge. You said these podium buildings are naturally problematic.
They are structurally irregular by their very nature. You have these massive stiffness discontinuities built right in.
And the number one risk?
Ignoring the soft story risk at the ground floor retail level. That is the single fastest way to design a failure. And that is the first hurdle we absolutely have to clear.
Okay, let's unpack this. It's technical, but it's foundational. Before a single line is drawn, before any architectural decision gets made, there's a code framework that sets the absolute floor for safety and performance.
Right. And the source material calls this the seismic funnel. It's a very structured process that tells you exactly how hard your building is going to have to work.
And where does it begin?
It begins with the site. You have to understand the specific hazard where you're building. That means defining the intensity of the potential ground shaking using two key numbers from the hazard map.
And these aren't just numbers plucked out of thin air.
Not at all. They come from decades of probabilistic modeling of ground motion. They are your starting point.
These are the famous 7 Zols and 7 L values. Okay, break that down for us. What? Two different numbers. Why not just one?
It's a great question. You have to think of a building like a giant tuning fork. It vibrates at a certain frequency or period. 7 Zols is the short period spectral acceleration.
Okay, short period.
Yeah, typically around 0.2 seconds. This number governs the forces that short, stiff, stocky things feel.
Like the columns in the podium itself.
Exactly. The columns, the beams in that heavy concrete base, or even the entire building if it's only a few stories high. It's the short, sharp, jerky motions.
Okay, so 7 Zola covers the stiff elements. What about 7 Zola?
7-1 is the 1 second period acceleration. This becomes critical for the taller, more flexible parts of the building, so the residential tower sitting on top of the podium. It characterizes that slower, sweeping, global sway of the whole structure.
So the earthquake hits the building with both kinds of motion at once, the sharp chop and the slow rock.
And you have to design for the worst of both. Absolutely.
And critically, those values aren't fixed. They get changed, sometimes dramatically, by what's underneath the building, the soil.
Site class, yes. This is a huge modifier, whether you're building on solid rock, which is site class A, or stiff soil, class C, or heaven forbid, on deep, soft clay, class E or F. It fundamentally changes how that seismic energy gets transmitted into your foundation.
And the lecture notes are pretty clear on this. Soft soil is the enemy.
It acts like jelly. It dramatically amplifies the ground motion, and it often concentrates more of that energy into the longer periods, which is, exactly what you don't want for your residential tower. You could have a site with a moderate seismic hazard, but if the soil conditions are terrible, it can easily push you into a very high-risk situation.
Okay, so once we have those numbers, the ground intensity, adjusted for the soil, the workflow becomes this very strict, linear path laid out by the code ASCE 7.
It's a true funnel. It leads you right to the constraints that will dictate your entire design.
What's the progression?
It goes from hazard, that's our size-allers, and site class, to the design response spectrum. That spectrum defines the required strength you need across all possible building periods. And that, in turn, gives you your seismic design category, the SDC.
SDC. A through F. And this is the
Now,
gateway.
the gateway.
But there's a crucial step in there.
Yeah.
One that really highlights the civic nature of this whole thing you were talking about. The risk category.
Yes. And this is where you, the design leader, have to make a decision that isn't really structural at all. It's about the building's purpose.
So most apartment buildings are what? Risk category 2?
Correct. Standard occupancy. But let's say you're designing a community center that's also going to be a post-disaster shelter. That's category 3. A major hospital or a fire station. That's category 3. In that designation, it automatically mandates a higher level of performance.
And what does that bump in category actually do to the design?
It can be huge. Depending on the underlying hazard, just changing a building from category 2 to 3 can automatically kick your SDC up a level. So you might go from SDCC to SDCD.
Which sounds like just one letter, but you're saying that's a massive jump.
It's catastrophic for the design process. It immediately shrinks the menu of permitted lateral systems you can even choose from, and it demands far more stringent, complex, and expensive detailing. The cost and effort can increase exponentially.
So, okay, let's assume we've landed in SDCD or higher, which is common for dense cities.
Yeah.
The code now gives us a limited menu of systems and tells us how much ductility they need. What does that SDC categorization really mean, conceptually?
It's a philosophical commitment. In SDC A or B, the code assumes the building can mostly stay elastic. It just has to be strong enough. It doesn't need to stretch much.
But in D, E, or F?
In D, E, and F, you're in a different world. The code demands that you choose a system that has proven ductility, which means you have to prove, through detailing, that your structure can yield, it can deform, it can even take on damage, but without collapsing.
And this choice, the system you pick from that menu, is what locks those performance numbers we always hear about. $3, 40D, and omega dollars.
That's right. Those 3 factors are the mathematical embodiment of your design trade-off.
Let's break them down. R, the response modification coefficient.
That's your ductility factor. It's a huge deal. It allows you to reduce the enormous theoretical earthquake forces because you're counting on the structure's ability to bend and not break, to yield.
So if I pick a really ductile system, like a special moment frame with an R of 8, I can design for much lower forces than a brittle system with an R of, say, 3.
Precisely. You're trading raw strength for the ability to stretch. But, and this is a huge but, that trade comes with a consequence.
Which is drift.
That's where CDAD, the deflection amplification factor, comes in. Because you've designed for lower forces, the building is going to move more. CDDs is the number you use to estimate the real displacement your building will experience as it yields. And you have to check that drift against strict limits.
And finally, omega 0, omega dollars, the overstrength factor. Why do we need to calculate how much stronger the system is than it's supposed to be?
Omega dollars is all about protecting the load path. You design your system to have a fuse, a specific spot, like a beam hinge that's supposed to yield first. But materials aren't perfect. Sometimes the steel is stronger than specified, or the load gets funneled in an unexpected way.
So the fuse might not blow where you want it to.
Exactly. Omega dollars forces you to make sure that everything else in the load path, the connections, the collectors, the foundations, is stronger than the strongest your fuse could possibly be. If a connection fails before the beam yields, your whole ductile strategy goes out the window. Those 3 factors, together, they lock in your building's structural identity.
Okay, so we've navigated the code funnel, we have our SDC, we have our performance factors locked in. Now we get to look at the actual menu of options, the systems themselves.
And every single one is a strategic trade-off. You're balancing structural efficiency, cost, and maybe most importantly for this building type, that need for flexibility on the ground floor.
The design of that podium level has to be the priority. You have to keep that big, open retail space, but you also need massive stiffness to handle the tower above it.
It's a fundamental conflict.
Let's start with the classic flexible option, moment-resisting frames, or MRFs.
An MRF is all about its connections. The beams and columns are connected rigidly so they can transfer bending moments. The whole frame resists lateral load by, well, bending.
And architects love them.
They do, and for good reason. They give you maximum freedom in your floor plan. You can have wide open spans, huge glass corners, total transparency. For a ground floor storefront, they're architecturally perfect.
But that flexibility, it has a price, both structurally and financially.
A steep price. Because they are so flexible, they're prone to large story drifts. So to control that drift, the connections have to be incredibly robust.
Especially in steel, right? The special moment frames.
In steel, yes. SMRFs require exceptionally heavy and complex detailing. You're talking about very specific pre-qualified welds, continuity plates inside the columns, and all of it requires intense, nonstop inspection. That makes them significantly more expensive to fabricate and build than other systems.
And in concrete, is it any easier?
Oh, it's a different kind of difficult.
Yeah.
In concrete, the joints are just unbelievably congested with rebar. You have to pack in tightly spaced hooks and stirrups to confine the concrete so it doesn't crush.
So it's a nightmare for the construction crew.
It can be. Pouring concrete into these dense cages of steel is a huge challenge. The risk of getting voids or honeycombing is very high, and a void in a critical joint compromises everything.
Okay, so let's contrast that immediately with the polar opposite. Braced frames.
Braced frames are the antithesis of MRFs. You add diagonal members, you create triangles, and the system resists load mostly through axial forces, tension, and compression.
Which is super efficient.
Incredibly stiff and efficient for the amount of steel you use. They give you excellent drift control, and they're relatively fast and cheap to erect. But they're architecturally invasive, severely invasive. That diagonal cuts right across the bay. It blocks views, it gets in the way of ducts and pipes, it completely dictates your interior layout.
So for a high-end condo with a corner view, a giant X-brace is probably not going to fly.
It's a non-starter. It's almost always a non-starter for this building type. You're forcing a compromise on the fundamental use of the space that most clients just won't accept.
Which brings us to the workhorse. Shear walls. The most common system we see in concrete mid-rises.
Shear walls are exactly what they sound like. They're deep, solid, vertical walls that act like giant cantilevers sticking out of the ground.
And the big advantage is their stiffness.
Extreme stiffness. They give you fantastic drift control. And, even better, they integrate naturally with the parts of the building you already need, the elevator shafts and the stair cores. These elements have to run vertically through the building anyway, so you just make them your lateral system.
It seems like the obvious default choice. But they have their own baggage.
They do. First, they're heavy. Really heavy. A lot of concrete adds a lot of mass, the W in our equation, which in turn increases the total seismic force V that you have to design for.
And the placement is critical.
Absolutely critical. If you don't place them symmetrically around the center of the building, you introduce that risk of torsion, of twisting, which we'll get into. And architects need to remember that you can't just punch holes in them wherever you want. A big doorway can severely compromise a shear wall's integrity.
So that naturally leads us to the hybrid solution, the dual system, a combination of frames and walls.
The dual system is an attempt to get the best of both worlds. You pair the stiffness and drift control of shear walls with the redundancy and the energy dissipation of a moment-resisting frame. This is very often the go-to choice for taller, more complex buildings in high seismic zones.
But the analysis gets much more complicated.
It does. The code has very specific rules. It demands that you prove both systems are doing real work. The frame, for instance, has to be strong enough to resist at least 25% of the total seismic force all by itself.
So you have to ensure they work together properly.
You have to model them very carefully to make sure they share the load as intended, especially at that critical transfer level at the top of the podium where the whole geometry changes.
So let's tie this back to that R-factor trade-off. Let's say I'm choosing between a special concrete shear wall and a special steel moment frame. How does that choice change my design demands?
The difference is fundamental. The steel moment frame, the SMRF, might have an R-factor of 8. That lets you slash your design forces, which is great, but it demands those hugely expensive, complex connections, and you're going to have high drifts that are hard to control.
Okay. And the shear wall?
The shear wall might have an R factor of 5 or 6, so you have to design for higher forces. That means thicker walls, bigger foundations. But because the system is so much stiffer, your drift is naturally much lower. That protects your non-structural components.
So it's a choice between spending money on complex labor and inspection or spending it on more concrete and steel.
That's it exactly.
Okay.
Are you buying ductility through complex detailing, or are you buying stiffness through sheer mass? It's a business decision dressed up as an engineering problem.
We've established this typology. The mid-rise mixed-use podium is the urban standard. But the very act of stacking that light residential tower on top of a heavy, open retail base creates one of the most infamous failure modes in all of structural engineering.
The stiffness discontinuity, or as the lecture calls it, the mid-rise trap.
And this isn't theoretical. We've seen this happen in earthquakes all over the world.
It's a classic vulnerability. Just visualize it. You have a thick, heavy, very stiff concrete podium, maybe 2 stories high for retail and parking. And then sitting on that is a much lighter, much more flexible structure for the residences, maybe wood frame or light gauge steel or thinner post-tension concrete slabs.
The danger is all concentrated at that one transition line.
Precisely. If you have a sharp drop in stiffness or a sharp drop in strength right at that level where the podium meets the tower, the building is at extreme risk of just hinging right there, of collapsing.
And historically, it's that soft story at the ground floor that's the killer.
It has been the primary cause of urban building collapse in major earthquakes time and time again. And it's driven by the architectural demand for those big, glassy, open retail spaces.
Let's focus on that retail level. Why is that floor inherently so much weaker and more flexible?
Well, what does a retail tenant or a hotel lobby want? They want maximum transparency, maximum openness, no columns in the way. Structurally, that means you have widely spaced, slender columns and almost no solid walls.
Okay.
But then you go one floor up into the residential levels. What do you have? You have dozens of apartment units, each with its own partition walls. Drywall itself adds a surprising amount of stiffness. You have a much denser grid of columns and walls. Those upper floors are exponentially stiffer than the open ground floor.
So the heavy, stiff residential block on top is trying to move side to side, and all of that massive displacement has to be absorbed by the weakest link in the chain.
The flexible glass box underneath.
That is the trap.
That is the textbook definition of the trap. The ground floor columns are forced to absorb all the lateral movement from the entire rigid mass above, which leads to concentrated deformation and catastrophic failure.
So the assignment requires students to propose fixes. What are the common mitigation strategies?
You have to ensure continuity of stiffness. It's not optional. This usually means putting very ductile moment frames at the ground floor, or strategically placing strong, heavily reinforced shear walls that align with the lateral elements in the tower above.
And if you can align them?
Then you need very big, very heavy, and very expensive transfer elements, massive beams or a thick transfer slab to physically drag the lateral loads from where they are in the tower to where your columns are in the podium. You simply cannot rely on the flexibility of that first floor to save you.
So that covers the vertical risks. But the code, ASCE 7, also forces you to check for horizontal problems. Let's dig into torsional irregularity.
Torsion, twisting. This happens when the building's center of mass and its center of stiffness don't line up.
Okay, analogy.
Imagine you have a cardboard box on a table. If you push it exactly in the center, it slides straight back. But if you push it on the corner, off-center, it spins, it twists. In a building, the earthquake force is like your hand pushing at the center of mass. The building's resistance comes from its center of stiffness, the average location of all your shear walls and frames.
And how do those two centers typically get misaligned in a mid-rise design?
It almost always comes from the architect's placement of the core. Let's say, to maximize views, the architect pushes the concrete elevator and stair core all the way to one side of the building.
Okay.
All of your stiffness is now concentrated on that one flank. So the center of stiffness gets pulled way over to that side. The opposite corner of the building, the one with all the glass and open space, becomes the flexible edge.
So when the ground shakes, the force pushes on the middle of the building, but the resistance is way off to the side.
And the whole building twists around that stiff core. The real danger is that the flexible edge experiences displacements that are hugely amplified compared to the rest of the building.
So that corner could easily exceed its drift limits and fail, even if the rest of the building is fine.
Exactly. The code has a specific check. If the drift at the far edge of the building is more than 1.2 times the average drift, you've triggered a torsional irregularity. And that forces you into much more complex and costly 3D dynamic analysis. You lose the option to use simpler methods.
So the lesson for the design leader is that a simple, boring, symmetric plan is actually a very smart, robust, and cost-effective plan.
Absolutely. Running these checks, soft story, weak story, torsion, it's not just a box-ticking exercise for the code, it's a fundamental step in resilience planning. If you can design these irregularities out of your building from the beginning, you've ensured it will perform in a much more predictable and safe way.
Okay, so we've conceptualized the force. V equals CS times W. It's this enormous lateral load pushing on the side of the building. Now we need to talk about the choreography of getting that force safely from the building down into the ground.
The unbroken load path.
Yes. And this is where we shift from thinking about the size of the elements to thinking about their connectivity.
It's so critical. It's not enough for your shear wall to be strong. It has to be continuously connected to everything else. One bad link, one failed connection can compromise the entire system.
The source material lays this out as a 5-step chain. Let's walk through it. Step 1. The energy hits the floor diaphragm.
The floor slab, whether it's concrete or a metal deck, has to act as a single, rigid, horizontal plate. Its job is to collect all the inertial forces from that level of the building and distribute them horizontally.
And if the diaphragm is weak, if it has a giant hole in the middle for an atrium,
then it can't do its job. If the connections between the floor and the walls are weak, the diaphragm will just tear away, and the walls will never even feel the load they were designed to take.
Okay, so the diaphragm collects the force. Step 2 is getting that force to the vertical elements using collectors. This is a concept that I think a lot of non-engineers miss.
They are fundamentally critical, and often called drag struts. Imagine your floor slab is 100 feet wide, but your concrete shear wall is only 20 feet long. How do you get the force from the whole width of the slab into that narrow wall?
The collector.
The collector. It's usually a heavy beam or a thickened band of reinforcement in the slab that literally drags all that dispersed force and funnels it, concentrates it, right into the ends of the shear wall.
This sounds like a prime location for a coordination error with, say, plumbing or HVAC.
A classic hotspot. You can't just cut a hole in a collector beam for a pipe. The reinforcement in these elements can be extraordinarily dense because they're handling massive tension and compression forces on top of gravity. If a collector fails, the diaphragm effectively disconnects from the shear wall.
Okay, so step 3 and 4 are the main players. The collectors dump the force into the vertical shear walls of frames,
which have to carry it continuously down, story after story, to the foundations. Any offset in a shear wall from one floor to the next requires a huge, expensive transfer girder. You want a straight, clean shot down to the ground.
And the final step, step 5. The foundations transmit all that collected force into the soil.
And the soil has to be able to take it. If your foundation isn't designed properly, or if the soil itself liquefies, then that immense base shear force has nowhere to go. It must be a continuous, unbroken chain from the roof all the way down to solid earth.
So for the design leader, the takeaway is that structure isn't just about stacking things vertically. It's about ensuring that horizontal connectivity is perfect at every single level.
That's the essence of it.
Now let's talk about the result of this load path in action. Drift. You mentioned it before, the story-to-story displacement. Why do engineers seem to worry about drift even more than they worry about strength?
Because strength is about life safety. Strength is what keeps the building from collapsing. Drift is about serviceability. Drift is about whether the building is usable or even repairable after the earthquake.
And it's where most of the money is lost.
The vast majority of economic loss in modern earthquakes comes from excessive drift.
So what are the actual financial consequences of blowing past your drift limit?
The code puts limits on drift, say, 2% or 2.5% of the story height, to protect the most expensive and brittle parts of your building, the non-structural components. If you have too much drift, your exterior glass curtain wall shatters, your interior drywall partitions crumble, elevators get jammed in their shafts, expensive mechanical equipment on the roof tears away from its piping.
So even if the concrete and steel are perfectly fine, the building is a total loss.
It can be. The repair bill for all the non-structural damage can easily be 80% of the building's value.
And this brings us right back to that fundamental trade-off. Choosing a high R-factor system saves money on structure, but it means you accept higher drift.
Which means you have to spend that money elsewhere. If you choose a very flexible high R system, you have to spend a fortune on designing flexible non-structural connections. Seismic joints for your pipes, special glazing gaskets, drywall details that can accommodate movement.
Versus a stiff system.
If you choose a very stiff system, like thick shear walls, you spend more upfront on the concrete and rebar, but your drift is minimal, so your secondary costs are protecting the non-structural components go way down.
The ultimate performance goal, though, isn't just about limiting damage. It's about minimizing residual drift.
That's the key to resilience. Residual drift is the permanent tilt of the building after the shaking stops. If a building is left leaning more than about 0.5%, it's often considered irreparable. It's a teardown.
So resilient building is one that snaps back to vertical.
So that it can be quickly inspected, repaired, and reoccupied. For a commercial building owner, that's everything. Protecting your net operating income, getting tenants back in, and rent flowing, that is the true financial benefit of investing in rigorous drift control.
It's one thing to make these decisions on paper, to look at R factors in a spreadsheet. But when you take a high ductility design out to the construction site, the reality of actually building it can be a rude awakening.
It's a huge commitment. When you choose a system like a special moment frame or a special shear wall, you are committing to a level of complexity in the field that is orders of magnitude higher than standard construction.
Why is that?
Because ductility isn't something that just happens. It has to be meticulously built in through very precise detailing. Detailing that is designed to confine the concrete, to prevent brittle failure, and to force the steel to yield in a predictable, controlled way.
So paint a picture for us. What does this actually look like for the iron workers, for the concrete crew on site?
In a concrete shear wall, especially at the ends, what we call the boundary elements, the rebar cages become almost solid steel. You have stirrups spaced every few inches, you have specific 90-degree and 135-degree hooks, you have very precise lap splice lengths.
And trying to pour concrete into that.
It's incredibly difficult. The space between the bars might only be an inch or two. You have to use very flowable concrete mix, and you have to vibrate it perfectly to avoid creating voids or honeycombing. A single void in that critical boundary element can completely compromise the wall's performance.
Which means inspection can't be an afterthought. It'd have to be a primary budget item.
It mandates what's called special inspections. This isn't the city inspector showing up once a week. This is a third-party inspector on site, full-time, whose only job is to verify that every single piece of rebar is in the right place, that every weld on a steel frame is perfect, that the concrete is being placed correctly.
That sounds expensive.
It is. It adds significant time and cost. But it is the absolute ethical requirement. Without it, you have no guarantee that the ductility you calculated in the office actually exists in the real building.
And the coordination headaches must be at their worst at those transfer levels, like the podium slab.
Absolutely. That transfer slab, or those transfer beams at the podium, are the coordination hotspots. They are massive. They are collecting all the gravity load from the residential grid above and all the lateral force from the earthquake. The amount of rebar in them is staggering. We're talking about beams that can be 4, 5, 6 feet deep.
And if your structural elements are that big, clashes with the other trades are pretty much inevitable.
They are. The MEP systems, your big HVAC ducts, your main plumbing lines, they always want to take the easiest path. And that path is often right through the middle of your most critical structural member.
So you get call from the site saying the plumber needs to core drill through your main collector beam.
And the answer has to be no. If that coordination isn't done down to the inch in the design phase, you end up with these terrible choices on site. Either a massive change order to reroute all your utilities, or someone makes a field modification that secretly weakens your entire lateral system.
Which brings us to the final part of this, the ultimate test of leadership, the trade-off between first cost and long-term life cycle resilience.
This is the financial core of the ethical problem.
When you're in that value engineering meeting,
Yeah.
and the pressure's on to cut costs, it's so easy to shave a bit off the seismic detailing.
It's the easiest thing to cut because it's complicated and the client doesn't see it. Maybe you choose a simpler system, or you decide to tolerate a little more drift because it still technically meets the bare minimum of the code. But what you're really doing is making a direct investment in future damage.
Let's make this real. Let's imagine two identical buildings, A and B, side by side.
Okay, building A, the team cut corners. They used ordinary detailing instead of special detailing to save some money. They ignored a small torsional irregularity because it was too complicated to analyze properly. A major earthquake hits.
Does it collapse?
No, it survives. The code worked. People got out alive. But the uncontrolled drift caused immense damage. The non-structural systems are destroyed. The building has a permanent lien. It gets red tagged. It's closed for 3 years while they figure out how to repair it, if they even can.
And the cost of that is borne by the whole community.
Exactly. The residents are displaced. The businesses on the ground floor are bankrupt. The city loses tax revenue. Now look at Building B right next door. The team invested up front. They used a robust dual system. They paid for the complex detailing. They designed for tight drift control.
And when the quake hits,
The building performs exactly as designed. The damage is localized, it's repairable, the residual drift is negligible, the building is inspected, cleaned up, and it reopens in 3 months.
The difference between 3 years of displacement and 3 months of inconvenience.
That is the entire ethical and financial metric for a design leader. Your system choice is a value statement. Are you just designing for code minimum life safety, which means people don't die? Or are you designing for maximum community recovery speed and economic continuity?
Because true leadership means understanding that it's the most vulnerable populations that get hit hardest by displacement and downtime.
They're the ones who can't afford to be out of their homes or their jobs for years. You are designing a piece of civic infrastructure. It has to hold the community together, not just itself. Hashtag tag outro.
Well, this has really driven home that seismic system selection for these buildings isn't some marginal engineering task. It is a completely unified, ethical, technical, and financial decision that genuinely shapes a community's future.
Right. And the competency that the DBSK assignment demands is that you move beyond just passively accepting the code. You have to be able to choose a system MRF, shear wall, dual, and then rigorously justify why it's the right choice for your building's SDC and its program.
And you have to show you understand that unbroken load path. You have to be able to sketch it out conceptually, from the diaphragm through the collectors all the way down to the foundations. And you have to prove you've analyzed and mitigated those key risks of soft story and torsion.
And the curriculum doesn't let you stop there. The next step is to immediately fold those seismic decisions into everything else. The location of your shear walls dictates your floor plan and your exterior envelope. The depth of your beams impacts your MEP routing. Structure does not live in a silo.
So we'll leave you with this final thought, which is really the ultimate test of leadership from this lecture. Do you optimize for first cost, or do you optimize for community resilience?
The architect-builder-statesman understands their duty is to the long-term health of the city. Every single seismic decision you make communicates your values. When that inevitable test comes, how much damage is acceptable to you? And are you sure your community won't be the one paying the price for design shortcuts with their homes and their livelihoods? Now, what system will you choose?